Hello everybody. So we have been discussing the Fujinobu model, right? And we saw how you can reduce the 4-variable Hodgkin-Huxley model to 2 variables by making some assumptions, and you can do baseline analysis and show some interesting effects with a simplified model that's a Fujinobu model. So just to recap, what we have done so far is we have derived the null planes, and we have shown that the V null plane has this kind of an inverted N shape, and the W null plane is simply a straight line. So when IA is equal to 0, this is how it is. And in this condition, also particularly in case of Fujinogumo, the W null plane, the values are low, much lower compared to the V null plane. So therefore, most of the flow is in the horizontal direction. So if you start from here, you just roll back to the origin. But if you start from here, you climb up and come back, and so you produce a kind of a distinct action potential like response. Uh, so that's what happens when IA is 0. And as you increase the input current, you are basically lifting up the V null plane, which might then let us say this is like this, and your V null plane is like that, right? And this is W null plane. So if they intersect in this middle branch, so we identified 3 branches in the V null plane. The left branch, number 1, the middle branch, number 2, which is between the minimum and the maximum, and the right branch, which is number 3. Okay, if the intersection happens in the left branch, so we've seen that it all depends upon the, so if f prime of V, right, is less than B by R, okay, then the delta is positive, right, and if f prime is itself positive, then tau is also positive because tau is equal to this. So therefore, so that is what happens in the middle branch, because here f prime is negative, here f prime is positive. So the point becomes unstable, and it turns out that it is a unstable focus, but we're not deriving it here. And at this point, you have circulating current, and you also have a limit circle. So that is, which is what we have shown in the last class. Now we have one more interesting case, which you can guess very easily, right? Which is if you increase the current further, right, you will be lifting the, so this is your W null plane. You can lift the V null plane even further, and you will have a situation like this. So the W null plane, so this is VNC, this is WNC. These two intersect in the third branch, so the second branch. So at this point again, f prime is again negative, okay, and therefore this is always true. But tau is also negative. Right, so therefore, so this is a stable point, right? Just like the first point, but unlike the first point, you don't have any action potential kind of generation. So in this case, what happens is if the intersection happens like this, right? So the system simply goes to this point, and after that, even if you disturb it from here, right, it will all the flows, right, are simply directed towards that point. You just come back to that point. Okay, so this is just a numerical simulation of that. So this is the V null plane, this is W null plane. If you start V from any random value, it will just go to that point, right, and stay there. So it will, you can notice that. So normally so this is like the only resting state, right? And normally the resting state is either negative or a low value. So in this case, all the numbers are dimensionless, and we cannot compare them with the real values of -70 millivolts and all that. But basically, the resting state, if you look at the operating range of values for the voltage, the resting state occupies some of the lower values. That is the normal behavior. But in this case, the resting state itself is at a high value. It remains like that. So almost it's like a pathological condition. So, and this kind of a thing happens when, this kind of thing happens when the neuron is energy starved. Let me see if I have it written somewhere. Yeah, so this you can say it's a tonically depolarized condition. So neuron is like a permanently depolarized condition. So because V is positive all the time. So that happens when the neuron is energy starved. Okay, so next we have another interesting case, which is called bistability. So in the last three cases, we have seen that intersection happens either at right in the first branch or second branch or in the third branch. You can think of another case not by varying the input current, but by varying the slope of the W plane and make it look like this. So this is your V plane. Choose the slope of the W plane so that it goes something like this. Okay, so normally the slope is somewhat high, so it just intersects the V plane only at one point. But if you reduce slope, it will cut through this nonlinearity at 3 points. So you have three stable points. I'm sorry, three fixed points. Now we need to see which are stable and which are not. But you can easily imagine that the dynamics gets more complicated because of this. Because in all the three other previous cases, there's only one fixed point, right? All three cases. So here you have three fixed points. Now, what happens in this case? Let us say that we have three fixed points. So we call them P1, P2, and P3. So this is P1, P2, and P3. Let us examine the stability of these 3 points. So at P1, F prime is because P1 is at the first branch, so F prime is negative, and F so which is less than B by R. B by R is always positive. In this case, it's a bit low, but it is still positive. So therefore, delta is positive. Then tau is F prime, which is negative, so it is stable. So first point is stable. Similarly, the third point also has similar properties. Right, F prime is negative, and F prime is therefore less than B by R. So delta is positive and tau is negative. So this is also stable. But look at what's happening with the middle point, P2. In P2, we have a condition which didn't arise in all the other previous three cases. So F prime in this case is itself positive, which is okay, which is what we have seen even in case of the limit cycle, because in the middle branch, F prime is positive. But what suddenly happens in this case is F prime is greater than B by R for the first time, because the intersection is happening in a different direction. Okay, not like this, right? But not like this, but like this. So therefore, because of that, delta now becomes negative. And we know from our bifurcation map, right? If so this is delta, this is tau. If delta is negative, all this is saddles, right? And here you have, sorry, unstable and no stable. Okay, so you have a saddle node, right? Which means that here, if you start from somewhere here, you go to this point. If you start from somewhere here, you go to this point. Right? But you will find that there is an axis somewhere here, right? Where on that axis you move towards a point. But you know, if you perturbed off that, right, you move to either this point or this point. Okay, so this is called separatrix. Okay, I'm just approximately drawing it. I'm not saying this is exactly the angle of the separatrix or anything, but you will find a separatrix. So basically, the entire phase plane is divided into two regions, two basins of attractor. That's what it is called. So in one basin, all the points go here. In another basin, all the points go here. Okay, so you can see that in this simulation also. So you see that actually it's not very easy to see the intersection points because the graph is actually stretched out horizontally. But you can see one intersection point here, one here, and one here. Okay, somewhere here and somewhere here, right? And so therefore, depending upon the initial condition. So if we start from say point 4, it goes to 0, which is a lower fixed point. and if B starts from point 8, it goes to higher fixed point, which goes to 1. Okay, so this kind of property is called bistability, which means there are multiple, here there are two stable states. Sometimes bistability can be even more complicated. There can be two stable states. One could be a fixed point, another could be a limit cycle. So depending upon the initial condition, it can just fall into a fixed point and stay there forever, or it can get attracted towards a limit cycle and keep on oscillating forever. So that kind of bistability is also possible, but we'll see that kind of a thing later. But here we have a simpler kind of bistability where there are two stable fixed points, and the whole phase plane is divided into two basins of attractor, right, which are organized around those fixed points. Now, this kind of behavior is also interesting from a biological point of view, because there are neurons. So if you remember our initial description of the membrane potential, right, we have seen that the basic membrane. Uh, So the basic membrane potential is negative at -70 in the resting conditions. Right, if it's activated, it oscillates and produces action potentials. But in this case, the membrane potential can be in this tonically in this low voltage, or it can jump to high voltage and stay like that. Right, there is no action potential in this case. So this can happen also for certain parameter values, which is what the Pidgeon model is showing. And these kind of states are called, so this is called a down state, and this is called an up state. Now, interestingly, such neurons exist in the prefrontal cortex, and also this is in the cortex and in a place called striatum, right, which is it's a subcortical structure. Right, now, what is the purpose of these kinds of neurons? I don't know, some of you who have background in electrical engineering might have heard of something called flip-flops. Right, these flip-flops thing is they have the capability of latching. So if they have a state, if the flip-flop is uncertain, so there's a voltage, output voltage signal. If another input signal is say the set or reset, this voltage can remain in its previous state forever, and it can memorize it. Right, so you can latch your voltage value at the given value forever until you erase it again. So these are the kinds of units that you can use as memory devices. Right. So in principle, the neuron which is capable of remaining in this up or down states, right, is capable of behaving like can be capable of holding some information in memory. And interestingly, both prefrontal cortex and striatum have an important role in memory. Okay, so in memory and learning and memory, so which is interesting, but it's not a comprehensive statement, but it's just a comment. Let's say just a comment. Okay, so that completes our discussion of the Pidgeon model. Let us now discuss another similar model, right, or a simplified neuron model, which is low dimensional. This is called the Morris-Lekar model or ML model. Now, this is model not of a neuron, but of a barnacle muscle fiber. Right, barnacle is a sea creature. I don't know. The only place I have heard about this creature is in Tintin comics. You might have seen Tintin comics where this Captain Haddock keeps shouting, billions of blistering barnacles. So this is that barnacle, and this is a model of the muscle fiber in a barnacle. So the thing is, muscles and neurons, they have some common properties. So both are what are called excitable cells. So neurons and muscles are both example of excitable cells. Right, and you have different kinds of muscles, skeletal muscle, smooth muscle, and So skeletal muscle, cardiac muscle, that is muscle inside the heart, and smooth muscle. The thing is, physiologically, that is, if you look at it in terms of the exact ion channels present in all that, there could be differences among all these four different kinds of cells. But mathematically, people have often used very similar models to describe all the four. Because what is common to all of them is that they're electrically active cells, right? They produce some kind of action potential. Uh, and so also, the word excitable refers to the fact that they produce a nonlinear electrical response to input current, right? For example, just like neurons produce action potential, so that is when you give an input current, if your input current crosses a threshold, it suddenly produces an abnormal kind of disproportionate response, right? That is what is called excitability. So all these different kinds of cells are electrically active and are capable of getting excited, right? So therefore, it's people often study them and compare these different models. So if you look at the barnacle muscle fiber, it has so in Hodgkin-Huxley model, it is sodium potassium, voltage sensitive or sodium potassium channels. But it's not that that's the only way you can produce all this behavior. You can have other kinds of channels which are also voltage dependent. So in case of barnacle muscle fiber, it has a calcium current and a potassium current, and then leakage current. So instead of sodium potassium, they have calcium potassium and a leakage current. So therefore, let us look at how this works. So like before, here also you have a voltage equation, and so you have for potassium there is a uh, uh, so the potassium current is W, the notation for it is W, and then there's leakage current which is all in a constant, right? It's a constant current, I mean constant conductance. Now there is also a M variable which, like in case of FN model, we assume that that variable is fast based on its tau time constant values. That is, tau time constant is very small. So therefore, in this case, we just assume that m is equal to always m infinity, and thereby we replace the differential equation with a constant equation. So therefore, just like in case of Fujinobu model, here also you have only two differential equations: one for voltage, right, and another for W, that the second variable. And W dynamics is very simple. It's simply minus some factor phi times minus W plus W infinity. Now, like I said, M infinity is taken to be constant, and it's simply this thing. W infinity is also so no, it's not constant. W infinity is M infinity is taken to be like a function, right, of voltage like this, and W infinity is also a function of voltage, and and this is a tau for M infinity, for a W infinity. So basically, what is happening here is, if you look at our earlier analysis of single ion channel or a single of channel kinetics, right? There are two things. One is the gating variable. Then there is a so the gating variable has this kind of sigmoidal response to the voltage, to membrane voltage, right? And then the time constant simply looks like a bell curve. It's not a symmetric bell curve, but it's basically a bell curve. So what people do typically, just to simplify the calculations, is they express this always using some kind of a tanh function with some constant. It is a constant and some factor. So that kind of this formula roughly approximates all these different curves. Even if so this is an activation variable because it's increasing with increasing VM. Even if you have an activation variable, the same formula will work. So this is activation variable, this is Inac variable. The same formula applies to both cases. So because of that, you can have a kind of standard form to the equations. So similarly for tau also, since it's a bell curve, people approximate that using a Gaussian. So therefore, the advantage is if you have for a given channel, right, or for a given gating variable, if you want to have the formula for tau, the function of tau as a function of the membrane voltage, you simply use a Gaussian, and the only thing is you have to figure out what is the amplitude, what is the width, and what is the centroid of the person. Okay, so this is a standard practice. So that's why we are constantly seeing this kind of a tannage formula for the M infinity and W infinity. So with these assumptions, we have two null planes. The V null plane is given by setting the dV by dt term equal to 0, which means the sum of all the ionic currents will be equal to the external current IA. So if you take out W and move everything else to the other side, you get an expression like this. All right, so if you simply plot this as a function of V and W, you get some curve, and that is the V null plane. And then double null plane is very simple. It's simply a kind of sigmoid. Right, so let us see how these two things look. If you plot that, what is interesting is so W and V. V null plane again looks like this. Just like in case of Fujinogumo. Okay, so thing is, what is interesting is Fujinogumo is derived from Hodgkin-Sleeve model, which is a model of an axon. It's a neural membrane. Whereas this is from a muscle, right? But once you reduce the system, right, mathematically they seem to be very similar. And only thing is the double null plane is slightly different. It it's not a straight line, but it's a sigmoid. It looks something like that. Sorry, that's I don't know why I'm getting the straight lines. Right, so this is W null plane. So now again, just like last time, you can find out the fixed points, find out where it is intersecting, do stability, and analyze the behavior. So let us see that. So in this case, for external current in the range of 0 to 68, the intersection point is in the left branch. So here also you can divide the V null plane into left branch, middle branch, and the right branch. So again, you can do all the standard calculations. F prime here is negative, so it is therefore less than. So in this case, it is not B by R. The slope of the double null plane is not B by R, but this derivative of this curve at this point, and that is still positive. It's a bit low, but it is still positive because it is intersecting it from below upwards, right? So so therefore delta is positive, and then so tau is, so actually this is slightly different. So in this case, let me do the calculation. Yeah, so let me show the calculation. So if you look at this formula, right? If you want to do the stability analysis, you need to do, so the V null plane looks something like minus W plus you have this whole expression IA minus blah 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 by, so this whole expression is what I'm saying, by GK, etc., etc. Right. So similarly, W null plane is given by minus W plus W infinity. This whole thing is equal to 0. Okay. So the Jacobian will simply, so I'll call this whole expression f of V, right? And this expression I'll call G of V. So then what happens is Jacobian will be just dou F by dou V, and so this by W, right? W doesn't exist in this part. It is only here, so they have -1. Similarly, dou G by dou V, and this is -1. So if you look at these expressions, now calculate delta, which will be minus say F prime, right, plus G prime. Okay, and so delta greater than 0 means G prime is greater than F prime. That means slope of the double null plane is greater than the slope of the F null plane, the V null plane, sorry. So similarly, tau will be equal to f prime minus 1. So therefore, f prime is greater than 1 means tau is positive. Okay, so the conditions will be slightly different. So what happens is when here tau here the slope of this curve g prime is very small. It's non-zero. It's positive but quite small, and you can show that it is less than 1. So therefore, tau is negative, right? And therefore this point will be positive. It will be stable. This first and second point will be stable. So it's very similar to the previous case of what we saw in the Fujinova model, right? And therefore V will be stable. It will just go to a stable value and stay there. So that's like your resting potential. But if you increase the input current and take it to the range of 69 to 217 picoamperes, the intersection point now moves up and intersects the venal plane somewhere in the middle branch. When that happens, again, you can show that this point becomes an unstable focus. And in that condition, you will see that the voltage oscillates. There will be a limit cycle going around it. And so that if you plot the voltage component, it looks like this. This is continuous firing, and these are action potentials. And you can also see the characteristic shape of the action potential, a sharp rise towards a peak. And after that, it falls off more gradually. Okay, that's a typical action potential. And if you increase current even more to beyond 218 picoamperes, the intersection now moves over to the third branch. And again, you can easily do the stability analysis and show that this point is stable. And so in this case, if you again start V from any random initial condition, it will go to this high value and stay there. Because normally, a healthy neuron, resting potential is at a negative value. So in this case, this is for barnacle muscle, right? It is at what is so minus 37 or something like that, millivolts, something like that. But whereas in this case, it is resting state is at some 15 volts, millivolts, something like that. So this is actually a pathological condition. A normal neuron doesn't behave like this. Normal muscle also doesn't behave like this. Like I was saying in the previous model also, this situation occurs when the neuron is or the muscle is energy starved. So this is a sign that the cell is heading towards death. Okay, so this plot summarizes the behavior of voltage, a response of voltage as a function of input current IA or I applied current. So for I applied current less than this threshold value, okay, so you have only one fixed point, and that is negative as minus something millivolts. And as you keep on increasing current, that voltage value keeps increasing. And once it reaches the threshold value, suddenly dynamics changes. You have a bifurcation that occurs. The stable focus, right, which happened until then, suddenly changes to a limit cycle. So this is the limit cycle regime. And these two lines are actually the boundaries of the voltage. So basically, this part of the graph is saying that this is not a function, because a function means for a given input you should have only one unique output. That's what a function is. This plot is showing basically the bifurcations, right? These two parallel lines and two lines that are that exist here indicate the bounds of the voltage. So it's basically saying that voltage is oscillating between these two limits. So this goes on for some time. Even those limits also change. Lower limit increases, upper limit also increases. And as you change the input current further at about 217 to 18 picoamperes, the limit cycle stop. Another bifurcation occurs, and it is you have only one stable fixed point. And after that, it remains like that. And even that value increases slightly and slowly, but it continues. So this picture gives a summary of the dynamics of the Morris-Lacab model. Now let us look at then a third model, which is actually really shows very rich behaviors and quite complex. But I won't discuss all the properties of this because it's a very complex model. Although the equations are quite simple, they are in fact very similar to the previous two models that we discussed. But it can show very rich behaviors. So just to give a flavor of it, just the kind of things that are possible even with a simple two-variable system. I want to present some results of this another model. So this is called the Inapk model. So it has basically a sodium current and a potassium current, just like the Hodgkin model, but the actual current dynamics is, the ion channel dynamics is slightly different from the Hodgkin model. I'll see how it is, I'll show you how it is different. Okay, so this model is called Inapk model. The P stands for persistent. So persistent sodium channel, right? That's why it is called NAP. And there's also potassium channel. The sodium channel is called persistent because it has only an activation variable. So the original Hodgkin model in that the sodium channel has two kinds of gating variables: an activation variable M, inactivation variable H. Right. So because of that, as you increase voltage, the membrane voltage of the sodium channel, the voltage increases quickly and then falls rapidly also. Right. But because there's only an activation variable here, it increases. If you increase voltage, the channel opens and it stays like that. It doesn't close again. Right. There's no inactivation variable. But ultimately, it closes not because of the inactivation variables or gates inside the sodium channel, but it closes because of the potassium channel. Okay, because there's also a potassium channel, and this channel also has a single activation variable. So basically, in this case, you can easily see that there is a voltage variable Vm. Okay, and then there is a sodium variable and a potassium variable. And so we'll make some assumptions just like before and reduce it to two variables. So since there's no inactivation variable, that gating variable is gone. So you're left with three variables. But even these three will reduce it to two. So you can express it in general like this. So the voltage dynamics is simply given just like in the standard form, GNA bar into M, and even so in the original Hodgkin you have three activation gates and one inactivation gate, but here there's only one activation gate, so there's only M. It's not M cube. Okay, and the Gn similarly Gn here GK bar times N and GL. So okay, so very simple structure of the equation. So then you have M dynamics and N dynamics. So three equations. Now let us again, like before, get rid of M dynamics by assuming that it is a fast variable and tau is quite low. So then you are left with two equations, the V equation and the N equation. Okay. So therefore M is you got rid of the M dynamics by assuming that M infinity is always equal to this function of the voltage. Right, and tau is also, like I said, it's expressed as a Gaussian, right? And these are so V half, which is the transition voltage for M infinity, and so on and so forth. So you have two null clines. The V null cline is given like this. So this is obtained by simply taking this. You set this whole thing to 0, right? And then take N out. Right, express the whole equation and write it as a explicit function of x, function of n. Right, so it looks like this. Then n alkyne is simply, so this is minus n plus n infinity equals 0. That is n equal to n infinity. Now some of these things I am this neuron model, right? I am using from this excellent textbook by Izikevich called Dynamical Systems in Neuroscience. So this is figure number 4.4 from chapter 4 of this book. So just like before, again, so it's interesting that there is these patterns repeat for a wide variety of neuron models having very different kinds of ion channels, right? These patterns repeat. So in this case also the V null cline, the voltage null cline simply looks like an inverted N. And the N null cline again looks like, in fact, a sigmoid. In fact, if you go high up, you will see that it looks something like this. Okay, so it's again a sigmoid. So what happens is when these two intersect, so here also you have like three branches, right? So this is the left branch, middle branch, and the right branch. So in this particular plot, actually the intersection is occurring slightly to the left of slightly inside the left branch. And you can also show using very similar methods like what we have done before, that this point is stable. And if you start from there, it will remain like that. But what is interesting is, just like in the case of Fujinobu model, where although the intersection in Fujinobu you had it looked something like this. So although this is only a fixed point, right? If you start from slightly away from there, this is far slightly away from there, you make this long circuit and come back, right? So here also something similar happens, but it's slightly different in nature compared to the Fujinobu model. Because say for example, if you in the simulation plot, you see that if you start from here, so these are all points, right, which is on the horizontal line, which means that the n variable is constant, that is n naught is constant, but initial voltage V naught is varying, is text. So if you start from here, you make a small circuit and come to this point. You start from here, you make a longer circuit. Start from here, you make an even longer circuit, and so on and so forth. So point is, so start from here, it makes a very long circuit and comes back here. So there is, in case of the Fujinobu model, there is a clear threshold A, right, and there is a clear difference in the response for initial condition, initial voltages, which is less than this value, and initial voltage is greater than this value. But you see that in this case, there is no such distinct clear-cut threshold, right? As initial voltage increases, the response amplitude increases, but there is no clear demarcation line, okay, and which is very interesting about this particular model. And you see that in terms of overall equation, it's very similar to the Fujinobu model. It is just that the slight change in parameters. And one more thing about Fujinobu model is that the W dynamics is much smaller. That is, the B and R values are, since they're very small, most of the flow is horizontal. So that's why there is some kind of a threshold in voltage. But in this case, it is not the case. The flow in horizontal vertical lines are comparable. So therefore, because of this set of parameters and this configuration, you don't see a very clear-cut action potential. It's more gradual. It's nonlinear, but there is no clear threshold. The same thing you see even when you take like initial conditions like this. That is, initial voltage is all the same, but initial n value, n naughts are varying. So even then you see that, right, it is there's no clear-cut threshold value. Okay, so yeah. Then if you, just like in case of Fujinobu model, if you increase the current for the to the cell model, then the V null line is lifted up. So intersection occurs in the second branch, right? And in this case, just like this point becomes a unstable focus, and you have a limit cycle. I see that limit cycle has a very interesting contour. This is a limit cycle, and if you plot the V part of it, right, you see this this kind of a classic action potential. Okay, so we have seen three different models of simplified neuron models. So basically, in all these models, right, we take a cell model, right? It has a bunch of ion channels, and there are different variables which describe the dynamics. There is a membrane voltage, first of all, right? And then you have some gating variables, and whatever. You can have many of them because you can have many different ion channels and many different kinds of voltage gated channels. So these are the gating variables, and this is the membrane voltage. So this is the overall structure of any neuron model, right? Only now what we have done in the simplified neuron models is reduce them to two variables. Okay, and how do you reduce them? If it is slow variable, you just make it equal to some constant. If it is fast variable, okay, so fast means something like m equal to m infinity. So very slow means h equal to, right, some h naught. So these are the tricks that we used to reduce the number of dimensions, number of variables, and we did that until we left with only one gating variable. So at the end of it, we have been creating models where you have only two gating variables, two variables. One is the membrane voltage, and after that, just one more gating variable. Right. So this is simplified neuron models. That in all these simplified neuron models that we have created have the same kind of a structure. And not only that, it's not just the number of variables or even the type of variables. Once you have that, the V null line typically has some kind of inverted N-shaped profile. And the double null line has either a straight line or some kind of sigmoidal. Okay, so that's all. So this is a common feature. And even with this, there's immense variety of dynamics that you can produce. So I haven't shown you anything. What I've shown is just it's a tip of the iceberg. Because you can even have things like, other weird examples. You can have, uh, suppose this is your V null line. You can have your sigmoid going like this. Okay, so you'll have two fixed points here, another fixed point here, and you can have bizarre dynamics even with a simple model like this. So thing is, so you have also seen the neuron simulation, right, where you can have a neuron with lots of different ion channels, and you can do all sorts of simulations and all that. But even with a simple two-variable system, right, with which typically has one null line which is N-shaped null line, other is a Z-shaped or a sigmoidal null line. You have immense variety of behaviors, and you can exhibit a lot of behaviors that you see in real neurons, even with simple two-variable models. Okay, so that is something that we learned with these three examples, and these ideas are very well explained in Izikevich's textbook. Right, if you have time, take a look at that. So in the next class, what we will do is we'll take this kind of an agenda further, right, and show introduce a certain standard two-variable model, neuron model, which is defined by Izikevich, right, and so it has, in this case, at least the three examples that we have shown, the exact equations are not the same. They have roughly similar form, right, and the null lines are also similar in shape, but the exact equations are not the same. So Izikevich has actually observed these similarities and tried to standardize them and proposed as a kind of a standard neuron model, which has two variables, right? And using that particular neuron model, by simply varying the parameters, he showed how you can exhibit a wide variety of neuron dynamics or kinds of dynamics you see in real neurons in wide variety of species. Right. So, like I was saying, one of the things about one of the problems with current neuroscience is, we have like a huge kind of explosion of models, and for different phenomena, you have different models. There is no commonality, there is no integration, there is no unity, right? Whereas these are the kinds of methods or developments in computational neuroscience where people have tried to show like unified models which can explain, or single models which can explain a wide variety of phenomena. And these are the kinds of things we would like to emphasize, right, in particularly in this course. Thank you.